Welcome to the high-stakes table, focused learners. If you are sitting for the Cambridge Additional Mathematics exam, subject code 0606, or even 0580, 4024, 4037, and 4040, you already know that every single mark is absolutely crucial. Today, in this explainer, we are decoding quadratic functions. We are taking abstract algebra and translating it into clear, visual geometry. Think of it as playing the examiner's game and winning big. If you've ever stared at a complex mathematical equation in the middle of a past paper and wondered what it actually looks like in the real world or how to extract those hidden marks without panicking, well, you are in exactly the right place. By the end of this session, you are going to see algebra not just as a set of rules to memorize, but as a dynamic, visual map. You won't just be calculating, you'll be reading equations like a pro reads the table.
Okay, let's dive right into this explainer by exploring a concept that examiners use all the time to test your deeper understanding. We have this absolutely brilliant quote from the mathematician Sophia Germain, who lived from 1776 to 1831. She said, "Algebra is but written geometry, and geometry is but figured algebra." Now, what does she mean by that, and why does it matter for your exam strategy? Well, what she means is that these two branches of mathematics, which we so often learn completely separately in school, are actually just two sides of the exact same coin. When you are manipulating variables, moving x's and y's around in an equation to solve a problem, you aren't just shuffling letters on a page. You are literally stretching, bending, and shifting shapes into two-dimensional space. Our absolute focus today is on a very specific type of shape, the parabola, and the quadratic functions that create them.
But before we deal our first hand and look at the shapes themselves, it's absolutely vital to understand where our toolkit comes from. This whole journey started back in the 16th century, with a French mathematician and lawyer named François Viet. He was the original mathematical strategist. He revolutionized mathematics by pioneering what was then called New Algebra, where he started using letters and parameters to solve incredibly complex equations. I want you to really think about that for a second. He was solving equations of the second, third, and fourth degrees, discovering profound connections between positive roots and coefficients, and he did all of this completely without a calculator. He achieved his remarkable proofs using only a ruler and a compass. He laid the exact groundwork that allows us to look at an equation today and instantly know its geometric properties. He basically wrote the cheat code.
So, here is your mathematical success blueprint. This is exactly how we will build your toolkit today, breaking down how to navigate these curves step by step, so you know exactly when to hold, fold, or go all in. First, we will start by visualizing the curve. Then, we'll find its exact turning point, a classic exam requirement. Next, we'll unpack the ultimate tool, the quadratic formula. After that, we'll see how curves interact with straight lines through intersections and tangents. And finally, we'll solve quadratic inequalities, which is where so many students needlessly drop points. Let's get to it.
Right. Section 1. Visualizing the curve. Let's start with the most fundamental rule of the game, the visual shape of a quadratic expression. A quadratic function is a polynomial of order 2. That simply means the highest power of the variable you will ever see in the expression is an x squared. The absolute moment you see that squared term as the highest power in an exam question, an alarm should go off in your head. You instantly know the graph is going to be a parabola. It's either going to be a U-shape opening upwards or an N-shape opening downwards. There are no other options. But how do you know which one it is without wasting precious time plotting a single point? It's all about finding the dominant card in the equation. Think about the expression x squared plus 3x plus 2. When x is incredibly large, whether it's super positive or super negative, that x squared term completely dominates the rest of the expression. Because squaring a negative number makes it positive, the result pulls the ends of the graph infinitely up, creating a perfect U shape. Conversely, look at the expression 5 minus 4x minus 2x squared. Here, the negative 2x squared term is the boss. Squaring makes the x positive, but then multiplying it by that negative 2 drags the curve infinitely downward into an N shape. Look at the x squared coefficient, and you instantly know your graph's destiny. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving smoothly to Section 2, finding the turning point. Now that we know the overall shape of our curve, we need precision. We need to find that exact minimum or maximum tip, which we call the turning point. Every single quadratic curve has a perfect vertical line of symmetry, and the turning point sits exactly on this line. Finding this specific coordinate is one of the most absolutely crucial skills in algebraic geometry, and examiners test it relentlessly.
If the curve crosses the horizontal axis, we can easily find that vertical line of symmetry and the turning point by following these simple steps. Imagine you're in the exam hall and you see the curve y equals x squared plus x minus 6. Step 1, factorize it. It breaks down into x plus 3 times x minus 2, meaning it crosses the x-axis exactly at -3 and +2. Step 2. Parabolas are perfectly symmetrical, so the line of symmetry is exactly halfway between those roots. Add them together, -3 plus 2 is -1, and divide by 2, giving a precise midpoint of -0.5. Finally, step 3. Take that midpoint and substitute -0.5 back into the original equation to find your y-coordinate. You get -6.25. Since the x squared term was positive, we know it's a U-shape, so we've just algebraically pinpointed the exact minimum turning point at -0.5, -6.25. No graph paper required whatsoever.
But here is where the exam board likes to raise the stakes. What happens if the quadratic curve completely floats above the x-axis, or is buried below it and never actually touches it? The method we literally just used relies entirely on finding roots. If your U-shaped curve is floating high up in the positive y values, or your N-shaped curve is trapped in the negative y values, it will never cross the x-axis. There are no real roots to find. You can't factorize it. So how on earth do we find the turning point then? We need a much more robust tool for our arsenal.
Let's look at the ultimate ace up your sleeve, completing the square. This mathematical maneuver guarantees we can always find the minimum or maximum, regardless of where the curve sits. Take the expression x squared minus 8x plus 18. You absolutely cannot factorize it. So we complete the square. You take half of the x coefficient, which is -8, to get -4, and you square it to get 16. Now, break that positive 18 into 16 plus 2. Now rewrite the whole thing, x squared minus 8x plus 16 plus 2. That first part is a perfect square, compressing perfectly into x minus 4 all squared. Now, think about this logically. Any real number squared is either 0 or positive, so the absolute smallest that squared part can ever be is 0, which happens exactly when x equals 4. When that part is 0, the whole function just equals that dangling 2. Instantly, we have our minimum turning point. X is 4, y is 2. It's an incredibly elegant trick that perfectly reveals the hidden geometry.
Let's keep building. Section 3, the quadratic formula. When the completing the square method is generalized, it gives birth to the ultimate tool for finding roots. If you take the general quadratic equation, ax squared plus bx plus c equals 0, and you apply the exact same completing the square logic we just did, but using only those letters, you end up deriving something incredibly famous that every student must know.
This is the famous quadratic formula, where x equals -b plus or minus the square root of b squared minus 4ac all over 2a. The plus or minus symbol directly accounts for the two possible intersection points on the x-axis. Stop scrolling, subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Now, back to the formula. What makes this so truly powerful isn't just that it gives you the answers, it's that it contains a built-in diagnostic test for the geometry of the curve, and that diagnostic test lives right inside the square root.
So the absolute crucial point here is the discriminant, the b squared minus 4ac part sitting right under the square root. It acts as an instant diagnostic test for the curve's geometry. If it's greater than 0, the plus or minus sign gives you two real distinct values for x. Visually, that means the curve crosses the axis twice. If it equals exactly 0, adding or subtracting 0 changes nothing. You get one single repeated root, and the curve perfectly touches or kisses the axis just once. But if it's less than 0, well, you cannot take the real square root of a negative number. This isn't a math error. It's literally geometry telling you the curve completely floats above or below the x-axis, never touching it. It's brilliant.
Moving to Section 4, Intersections and Tangents. Now let's take these tools and up the stakes. We are going to apply them to see exactly how our quadratic curves interact with straight lines. We've mastered the relationship between the curve and the x-axis, but the x-axis is really just a specific, flat, straight line where y equals 0. What if the straight line is angled?
Think about this interactive challenge for a second. How can pure algebra tell us exactly what these two totally separate shapes, a straight sloping line and a U-shaped parabola, are doing on a graph? Imagine a line slashing right through the U-shape. intersecting at two distinct points. Or imagine it grazing the very edge, touching at just one single point, or floating entirely above it. How on earth do we test for this without drawing it out? Well, we merge them.
By solving the equations simultaneously, we force them to interact, merge them into one, and we can test it just like before. Let's do a quick mental data scan. Take the curve y equals x squared plus x and the line y equals 4 minus 2x. Step 1, we set them exactly equal to each other. Step 2, we rearrange everything onto one side to form a single new quadratic equation equal to 0. We get x squared plus 3x minus 4 equals 0. This new equation is mathematical magic. Its roots are the exact x coordinates where the line and curve collide. Factorize it into x plus 4 and x minus 1, and we instantly see the intersections happen at x equals negative 4 and x equals positive 1.
Now, what's really truly interesting about this slide, and where examiners love to award top marks, is how the discriminant saves us here. A zero discriminant means we have a perfect tangent. When we combine the line and curve equations, we just run the b squared minus 4ac test on the new merged equation. For instance, if setting a line and curve equal gives you a new equation where the discriminant is exactly 0, they don't cross twice. They touch at exactly one single point, making that straight line a perfect tangent to the curve. And if that new discriminant is negative, there are no real roots. Geometrically, the line and the curve completely miss each other in space. It is incredibly powerful to determine these complex spatial relationships using just basic algebraic arithmetic.
Finally, we arrive at Section 5, solving quadratic inequalities. Let's look at what happens when we don't just want a single point, but an entire range of values. This is where a lot of students find a flaw in their reasoning and lose marks. Sometimes you aren't looking for the exact moment an object hits the ground. You want to know the entire continuous window of time that the object is in the air. By quickly sketching the curve based on its positive or negative dominance, finding where it drops below 0 becomes a purely visual exercise. Let's solve the inequality x plus 1 multiplied by x minus 3 is less than 0. First, we pretend it's a normal equation to find the roots, which are negative 1 and positive 3. Next, we absolutely must imagine the shape. Expanding the brackets gives a positive x squared, so we know for sure it's a U-shape. Draw a quick horizontal line, mark negative 1 and 3, and sketch a U-shape passing perfectly through them. Where is this function strictly less than 0? Well, the U-shape dips below the horizontal axis exactly between negative 1 and 3. Therefore, our solution is the range where x is greater than negative 1 and less than 3. By turning the algebra into a quick picture, what looks like a complicated logic puzzle becomes instantly obvious.
I really hope this explainer has shown you that algebra isn't just a random collection of letters, but a beautiful logical map of geometry waiting to be decoded. From understanding whether a curve is a U-shape or an N-shape by looking at a single term, to finding exactly where it turns using completing the square, to testing its spatial relationship with other lines using the discriminant, you now have the tools to visualize the invisible. Think back to François Viet in the 16th century, figuring all of this out with just a ruler and compass. The tools he gave us allow us to confidently navigate mathematical space and play the examiner's game to win. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.